Welcome to math class. We are going to be continuing on in our Math Makes Sense 9 textbook. We're doing chapter 4, but we are going to be looking at one of the trickier skills in the Math 9 course, which is we have to actually write math equations to describe real life patterns. Okay? The other way I like to explain this is I'm translating into math from real life. Okay. We are looking at patterns and whether or not I can start writing my own equations that describe the patterns. So we're actually going to start by looking at the example on page 155, the landscape designer. So in there they've got a bit of a diagram and there's a few different plots of land. Okay? So what they're saying is this is a herb garden. These are wooden pieces of board that they're using to edge it. Okay? What we need to figure out is if I'm going to build a certain number of plots, how many boards am I going to need in order to build this completely and correctly? Now, simply, we can just count up the boards. We can draw a diagram like this, and I can just start counting up how many boards I'm going to need. But let's say, for instance, that this dude wanted to build 20 garden plots. That's a lot of boxes for us to draw, and then a lot of time spent counting. When instead, we can try and find shortcuts and let our math do the predicting for us. So the first thing I'm going to do is I'm going to write this information down in a table of values. So this table of values matches the information that we were given. So the number of plots, so in this one there's one plot, or the area inside the square. There's one plot, and I have 1, 2, 3, 4 boards. Where I've got 2 plots, I have 1, 2, 3, 4, 5, 6, 7 boards. So 7 goes in here. So on and so forth. When I have 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 boards for 3 plots, so on and so forth. I have 13 boards for 4 plots. So what I need to do is I need to write a mathematical equation so that I can go ahead and punch in any number and figure out exactly how many boards I would wind up with, regardless of how many plots I want to punch in. So what we have to do is look at the relationship between some of the numbers here. So if I'm looking at my plots, I have to look what's happening to my number of plots, right? So if I go from 1 to 2, this is plus 1 plot. From 2 to 3, plus 1. From 3 to 4, plus 1 as well. However, if I start looking at my boards, if I go from first to second, I'm going up 3. From second to third, here, I'm going up another 3. And I'm going up another 3. So there's a pattern involved here. And what we're saying is that there's a mathematical rule that every time this goes up by 1, this goes up by 3. So we need to find a way to show that in a mathematical equation. Okay, so my boards are going to equal the number of plots. Right? And then I need to have some sort of relationship that explains how many boards are going to be for each plot. Now I know that my boards are not exactly equal to my plots, right? 4 is not equal to 4. So I need to find a way to manipulate this. So let's go ahead and we're just going to start throwing things at the wall and see. So let's say what happens if we multiply this by 3? Okay, so my boards are going to equal the number of plots. So let's go ahead and try it with the first one times 3. Right? Now this gives us 3. Our actual answer is 4, so I know that this equation is not correct. Okay? However, I'm only off by plus 1. Okay? I'm going to go ahead and I'm going to try that same equation. Even though I know it's not right, I'm going to try and chuck it in there with a new number, and I'm going to see what I get. So P times 3. So my boards are going to be 2 times 3, so I get 6. This answer is not correct. We already knew that. Okay? 7 is our actual answer, but the question is, how much is it not correct by? Well, it's not correct by exactly positive 1. So that means up here, since it's off by plus 1 for this one and for the last one, I somehow need to figure out how I can add 1 to this equation. So I'm going to go back and I'm going to restart it again. Okay. Boards equals 3 times the number of plots plus 1. Go ahead and check it out. Let's try it with the number 3, as if we have 3 plots. So I've got 3 times 3 plus 1 equals 9 plus 1. So my number of boards is 10. Does that match with the number of values, or sorry, the table of values we have? Yes, it does. So 10 is correct. So I know that this equation is going to describe the mathematical relationship for this particular setup. Okay? I should also get in the habit of double checking more than one number just to make sure that it's working. So let's go ahead and try 4 as well. So 3 times 4 plus 1 equals 12 plus 1, which gives us 13. Is that the same as the number? Yes. So it's right. We have now just twice confirmed that that equation will give us the answer. Okay. Let's go ahead and take a look at another example here. So, take a look at the airplane example on page 156. Let's get rid of that. Okay. So what I have here is a plane that started cruising, or is cruising, at 10,000 meters. It's about to start coming down for a landing. And what they've noticed, or what they've measured, is the height of the plane every minute on its way down. Okay? So what they want us to do is find a way to come up with a mathematical expression that shows the relationship between time and height. Okay? So we're going to do this the exact same way that we did the last one. I'm going to look at what's happening to my time. So if I go from this one to this one, how much do I go up? Plus 1. From here to here, plus 2. Here to here, plus 3. Or sorry, I wind up with 2. But I'm having a bit of a brain fart. What I meant is plus 1, and this one also goes up, plus 1. This one goes down 300. This one also goes down 300. This one also goes down 300. So we've noticed a pattern. Our time goes down in blocks of 1 minute, and our height decreases in blocks of 300. So now I need to try and find a way to write an equation that expresses this, or sorry, write an expression that shows this. It might take a little bit of trial and error. So what I'm going to say is my height is going to be equal to, starting at 10,000, 10,000 minus 300. But I know that it's not just going down 300. I'm not stopping at 97. I know that every time I go down a minute, I go down another 300. So I need to put my variable for my time in there. I'm going to go ahead and try this one out. 10,000 minus 300 times 2 is 10,000 minus 600, which equals 9,400. So if I look over my table of values for number 2, my height is 9,400. Okay. I'm going to go ahead and try that. I'm going to double check it. We're going to go ahead and use the same spot on the board. So my height equals 10,000 minus 300 every minute. Let's do, oh, we don't have it, so let's try, oh, we do have it. Let's try 3. 1, 2, 3 minus 300 times 3. 10,000 minus 900 gives us 9,100. 1,000. Jeebus. What an atrocious rating that was. 9,100. Now, what I've got to do is take a quick look at my table of values. Is this number the same? Yep. So clearly, my equation or expression is correct. Okay. Moving on to our last example here. Kelly's cab ride. Now this is a legitimate, common type of equation that you're going to run into, especially if you're ever going to take a cab or any sort of ride sharing service. They're going to charge you based on this same idea. So what's going to happen as soon as you walk or get into a cab, $3.60 is going to immediately show up on the meter. If I get in the cab, they pull forward just a couple of feet and then I hop out again, they're still going to charge me $3.60. However, if I start driving a proper drive and actually go somewhere, they're going to start charging me $1.50 every kilometer that I drive. So what I need to do is come up with an expression or an equation that shows what my total could be depending on how many kilometers I'm going to be taking that taxi drive, right? So we're going to call f our big variable for f equals fare. Okay? I know right off the bat, every time I hop in the cab, they're charging me $3.60. So I'm going to put that in there. Now, they're not giving me a break in decreasing the amount of money, so I'm also going to add $1.50. And I'm going to go ahead and put a variable in for kilometers. Right? I'm going to say 150 per, and we're going to go K. So what they're saying is you're going to get charged $3.60 as soon as you get in the cab. Every time you, for every kilometer you drive, they're going to charge $1.50. Right? So I can test this out. Let's say that they go 10 kilometers. Okay. Oh, let's actually use the example from the book. Let's go with 11 kilometers. So all I have to do here is plug my variables in where they're supposed to be. So 360 plus 150 times 11. Give myself a little bit more room on the board here to work with. So $1.50 times 11 is going to give me $16.50. So I have 360 plus 16.50, which gives me a total of $20.10. The fare for 11 kilometers is going to equal $20.10. That's it for now. Go ahead and give that a try, and I will see you in math class.